Can you see my screen?
Yeah, we can, yeah. Well, but yeah, full screen would be nice. Yeah, thank you very much. Okay, we finish our first day of the workshop with one more talk on Peisert type graphs. And this talk is given by Sergey. Okay, the floor is yours.
Thank you very much. My talk somehow continues two talks and maybe extends two talks held today. The first talk by Chihoy and the second talk by Rees. My talk is also Peisert type graphs, and in the first talk, Chihoy told us about strict EKR property for almost all Peisert type graphs in some case. So my goal and my main direction is somehow dual to the first talk. We will discuss Peisert type graphs without strict EKR property, and as you remember, the definition of Peisert type graphs involves cosets. I will recall this definition in my talk. So if we talk about a Peisert type graph that does not have strict EKR property, then any Peisert type graph obtained from the generating set, obtained from this given Peisert type graph by adding new cosets in the generating set, will also not have the strict EKR property. So we meet the condition. We may define the condition of extremality of Peisert type graphs, and this is the first word in the title of my talk. And the extension of the talk by Rees is that in some special case of extremal Peisert type graphs without strict EKR property, we will show that these extremal graphs are isomorphic to a special subfamily of hyperbolic affine polar graphs, and using this isomorphism, we may show that we can show that in some case, in this case for the negative, Rees told us about the positive non-principal eigenvalue, but in my talk we will meet the tightness of the weight distribution bound for the negative non-principal eigenvalue of affine polar graphs. It's interesting that it is not clear how to establish the tightness of the weight distribution bound for affine polar graphs in that case directly. I mean, working with the usual definition of affine polar graphs, but this result somehow arises very natural when we deal with extremal Peisert type graphs that are isomorphic to this special family. So my talk is an extension of the first two talks today, and this work is joint and it's in progress, and my colleague is Chihoy. Let me start from basic definitions. Let P be a prime and Q be a power of P. Let FQ be a finite field with Q elements. FQ plus be its additive group, and FQ star be its multiplicative group. Given an abelian group G and a connection set S, which is a subset of G minus 0, with the property that S is inverse closed, the Cayley graph K of GS is the undirected graph whose vertices are the elements of G such that the vertices G and H are adjacent if and only if the difference G minus H belongs to S. And we Peisert type graphs are Cayley graphs over the additive group of a finite field of square order. So this is why these two notions appear on the same slide. Let S be a union of M cosets of FQ star in FQ squared star, where M is at most Q. That is, S is equal to the union C1 times FQ star join C2, union C2, FQ star, so on, union CM, FQ star. Then the Cayley graph K of FQ squared plus S is said to be a Peisert type graph of type MQ. So the first parameter M is the number of cosets involved in the connection set, and Q is the size of the subfield. But the whole Cayley graph is over FQ squared star, over the additive group of the finite field of order Q square. Let us give some comments which were also given by Chihoy. While Peisert type graphs were introduced formally recently, see these two papers, they can date back to the construction of cyclotomic stronger regular graphs due to Brouwer, Wilson, and Xiang around 20 years ago. The definition of Peisert type graphs is motivated by the well-studied Paley graphs and Peisert graphs, which are only defined in finite fields with odd characteristic. However, the definition of Peisert type graphs naturally extends to finite fields with characteristic too. Let us discuss how the class of Peisert type graphs intersect with some known interesting families defined on the elements of a finite field. Paley graphs of square order are always Peisert type graphs. Peisert type graphs, P star of Q square, where Q square is congruent to 3 modulo 4, are Peisert type graphs. And we know that not all Peisert graphs are Peisert type graphs. The general definition of a Peisert graph says that Q is equal to P in some power. So the underlying prime number P, such that Q is a power of P, must be congruent to 3 modulo 4 in the general definition of a Peisert graph. But here we consider a special case when Q is congruent to 3 modulo 4, and we consider the graph P or P star of Q squared. Generalized Paley graph GP Q squared D, where D divides Q plus 1. Chihoy mentioned this case in his talk, and where D is greater than 1. And we also mentioned that not all generalized Paley graphs are Peisert type graphs. So only the case show it on the slide, shown on the slide. And generalized Peisert graphs GP star of Q squared D, where D divides Q plus 1 and D is even. And we also mentioned that not all generalized Peisert graphs are Peisert type graphs. Let me recall that for the clique number omega of X of a strong irregular graph X, the Divisors-Hofmann bound holds. The clique number is at most 1 minus k over theta mean, where theta mean is the smallest eigenvalue of X. A clique in a strong irregular graph is a Divisor clique if its size is equal to the Divisors-Hofmann bound. Peisert type graphs are known to be strong irregular graphs, and Divisors-Hofmann bound implies that the clique number is at most q. From the decomposition of the connection set into fq star cosets, it is clear that translates of C1 fq, C2 fq, so on Cm fq are Divisor, and in particular maximum cliques in X. So this M cliques C1 fq, C2 fq, and Cm fq are exactly okay. So these cliques contain 0, and we speak about translates of these cliques, so about additive shifts of these cliques, and any such an additive shift is known as a canonical cliques. So these cliques, the additive shifts of these M cliques, including of course these M cliques, are called the canonical cliques in X, and we say that X has the strict EKR property if all maximum cliques in X are canonical. Such a terminology is reminiscent to the classical Gorges theorem, where all maximum families of k-element subsets of an n-element set are canonical intersecting sets whenever n is greater or equal to k plus 1. There are lots of combinatorial objects where an analog of the Gorges theorem holds. We refer to the book by Gotzel and Marr for a general discussion on EKR type results. And let us discuss some results on Peisert type graphs. The first one was shown recently by Shamil Asgarli and Chihoy Irg. Let X be a Peisert type graph of type MQ, where Q is a power of an odd prime P and M is at most Q plus 1 over 2. Then any maximum clique in X containing 0 is an FP subspace of FQ squared. So the canonical cliques in Peisert type graphs are, of course, FP subspaces of FQ squared. But this result is very interesting, and it will help us to deal with extremal Peisert type graphs. Let X be a Peisert type graph of type MQ without strict EKR property. We say that X is extremal if all Peisert type graphs of type M-1Q have the strict EKR property. So as we already discussed, if a Peisert type graph does not have the strict EKR property, then any Peisert type graph obtained from this graph by adding more cosets to the generating set, to the connection set, will also have no strict EKR property. So in other words, we say that a Peisert type graph X is extremal. A Peisert type graph of type MQ is extremal if M is the smallest number of cosets such that a Peisert type without strict EKR property exists. And recently we proved the following theorem, which will be extended in this talk. If Q is greater than m-1 squared, then all Peisert type graphs of type MQ have the strict EKR property. Moreover, when Q is a square, there exists an extremal Peisert type graph of type square root of Q plus 1Q without the strict EKR property. So the second part of this theorem will be extended. However, our proof of the existence of such an extremal Peisert type graph was not constructive, and so an explicit construction of extremal Peisert type graphs of type square root of Q plus 1Q without the strict EKR property was not given in this paper. And the main problem of this talk is as follows: determine all extremal Peisert type graphs without strict EKR property. And let me give an outline. In this talk, we investigate extremal Peisert type graphs of type MQ and consider the following cases: Q is prime, Q is not prime. If Q is prime, we will see that the classification of extremal Peisert type graphs will follows from some known results on directions in affine planes AG to P, where P is prime. And if Q is not prime, our results do not follow directly from any known results. So then U and our new results consist of the following parts. We give a bound B of Q for M and show its tightness. Then we show a uniqueness of the extremal Peisert type graph without strict EKR property in case when Q is a square. We also show a uniqueness of the extremal graphs in case when Q is a cube but not a square. And we will discuss a special case, the smallest case when Q is not a square and is not a cube. So the fifth power of 2, Q is equal to 32. And it turns out that there are exactly 2 extremal Peisert type graphs in this case. So this makes the problem formulated on the previous slide more interesting. And we also discuss some related problems. Let U be a subset of AG2Q, affine plane AG2Q. The set of directions determined by U is defined to be the following set. For any A, B, and C, D points of U, we collect projective points containing this affine points. So we collect the following projective spaces generated by pairs A minus C and B minus D, where A, B, and C, D are the affine points, such that A, B is not equal to C, D. The theory of directions has been developed by Redday and Sonyi and many other authors. It is of particular interest to estimate the size of the set of directions of a subset U. And this theorem is about the sets of directions in the case when the order of our affine plane HG to Q is prime. So we consider the case when Q is equal to P is prime, and we consider the sets U whose size is equal to P. If the points, the first theorem is the first item of this theorem is due to Rede. If the points in U are not collinear, then U determines at least P plus 3 over 2 directions. The second item is by Lowash and Schreiber. If U determines exactly P plus 3 over 2 directions, then U is affinely equivalent to the following set of points, where X runs over Fp, and the third item is due to Gax. If U determines more than P plus 3 over 2 directions, then it determines at least the floor of 2P plus 1 over 3 directions. So for our purposes, the second item will be more interesting, will be the most interesting. And here is our first corollary. If Q is prime and Q is greater or equal to 7, then there exists a unique up to isomorphism Peisert type graph of time Q plus 3 over 2 Q that fails to have the strict EKR property. And moreover, this graph is extremal. It is not written on the slide, sorry, but I should mention that it also falls. So somehow the case when Q is prime is somehow the case when Q is prime is completely solved. And let us present the bound for extremal Peisert type graphs for the parameter m of them. Let Q is equal to P to the power of n, where n is greater than 1. And let K be the largest proper divisor of n. Then any Peisert type graph of type MQ has the strict EKR property, provided that m is at most p to the power of m minus k. Moreover, in a Peisert type graph of type such that the number of cosets is one more comparing to the bound, each maximum click containing 0 is fp to the power of q subspace in fq squared. So this is improvement of the result by so for this case, this is an improvement of the result by Shamil and Chikhoy, who showed that such a maximum click has to be an FP subspace. So we denote by B of Q the number P to the power of n minus k, and this is our bound. Let us introduce an important family of graphs YQN in the frame of this talk. Let Q is equal to R to the power of n, where R is a prime power and n is prime. Assume that FQ squared is written as the set of elements x plus y beta, where x and y run over FQ, and where beta is a root of an irreducible polynomial. F of t over FQ. So maybe this is not such a polynomial is reducible when d is a non-square and q is odd, but some similar polynomial can be also used in the case when q is even. So this polynomial is for the case when q is odd, but when q is even, the situation is similar. And considering f r to the power of n as an n-dimensional fr vector space, underline the affine space Hg and R, let H be an additive coset of an n-1 dimensional subspace in Fr to the power of n. Equivalently, let H be a hyperplane in the affine space Hg and R. Note that the size of H is R to the power of n-1. And we use this subspace to define the generating set of our Peisert type graphs YQN. S of H is equal to the union of two parts. The first part is just FQ star, so the coefficient C is equal to, say, to equal to 1 in this case, and the second part is the union over all H small running over H capital, and the coefficients C are given by H plus beta. Okay, so the only appearance of H in this definition is in the second part of S. And let YQN of H be the Peisert type graph of type R to the power of n-1 plus 1, comma R to the power of n, defined by the generating set S of H. In fact, S of H contains exactly R to the power of n-1 plus 1 cosets. The first coset is given by FQ star, and R to the power of n-1 cosets given by the second part of S. And one more result we have obtained in our work is that for any two hyperplanes H1, H2 in Hg of NR, the graphs YQN H1 and YQN H2 are isomorphic. And we write, if we meet only the isomorphic class of these graphs, we write YQN, just YQN instead of YQN of H. And let us ask a question: given a prime power Q, how many graphs YQN have we defined? Because you might notice that we started with the condition Q is equal to R to the power of n, where R is a prime power, such that Q is a power of this R, but some prime powers Q can be written as R to the power of N in where R is a prime power and N is a prime in different ways. And let us discuss how many ways to write down Q in such a way do we have. Let Q be equal to P to the power of M, where P is prime and M is an integer, M is greater or equal to 2. Let D be the number of different prime divisors of M. We have defined exactly D graphs Y Q of U. It should be not just Y Q and one more parameter, which is different. It means that for given Q, we have defined exactly D graphs YQ, where D is the number of different prime divisors of M. Indeed, let K1, so on KD, be the divisors of M such that M over K1, so on M over KD are different primes, and let us sort them in increasing order. Maybe better to say, exactly, in increasing order. Then we put Ni to be equal M over Ki and Ri be equal to P to the power of Ki. Then for any I from 1 to D, Q is equal to Ri to the power of Ni, where Ri is a prime power and Ni is prime. And we have defined the graphs YQ and 1, so 1 YQ and D. So on the next slide, we show that this the graphs YQN do not have the strict EKR property, and so we can formulate a problem: are these graphs minimal in terms of not having strict EKR property? So some of them are not. So given a prime power Q, only one of these graphs is extremal, and the other D-1 graphs are not extremal, but they do not have the strict EKR property, and it's reasonable to ask whether these graphs are minimal in the sense of not having strict EKR property. And one of our main theorems in this talk is as follows: let Q to be equal to R to the power of N, where R is a prime power and N is prime. Consider the graph YQN. The graph YQN is a Peisert type graph of the following statements hold. The graph YQN is a Peisert type graph of type R to the power of N-1 plus 1, comma, R to the power of N, and this graph fails to have the strict EKR property. And we conjecture that YQN has exactly R to the power of N-1 over R-1 non-canonical cliques containing 0. So we plan to describe them and show this conjecture. We are sure that it is true. And here is one more theorem, which can be described as a classification of extremal Peisert type graphs without strict EKR property in some cases. Let Q be equal to the P to the power of M, where P is prime and M is an integer, where m is greater or equal to 2, let k1 so on kd be the divisors of m such that m over k1 so on m over kd are different primes, and they are sorted in increasing order. Let us put that n is equal to the smallest value, to the smallest prime divisor m over k1, and r1 to be we put r1 to be equal to p to the power of k1, then the following statements hold. The graph yqn1 is an extremal Peisert type graph without strict EKR property, and if n1 is either 2 or 3, then yqn1 is the only up to isomorphism extremal Peisert type graph without strict EKR property. So in the cases when we treat Q as a square or as a cube, we have a classification of extremal Peisert type graphs without strict EKR property. But further classification may be challenging. If Q is equal to 2 to the power of 5, so Q is 32, then there exists exactly two non-isomorphic extremal graphs without strict EKR property. One of them is y32, 5, and we have one more. And we conjecture that if n1 is prime such that n1 is greater or equal to 5, then there exists at least two non-isomorphic extremal graphs without strict EKR property, and our goal to classify all of them. Let us discuss graphs yq2 in more details. Let q be equal to r squared, where r is a prime power. Note that fr is a hyperplane, so just a line in the affine plane AG of 2r, and we consider the extremal Peisert type graph q2 of fr of type r plus 1q. It follows from the classification that it's unique up to isomorphism. We have put h to be equal to fr in the definition of q2 of h. And let us define one more graph, one more Peisert type graph with the same parameters denoted by xq. Let xq be the Peisert type graph of type r plus 1q defined by the generating set S, where S is a union of cosets given by the values delta plus beta, where delta runs over q, where q is the set of all non-zero elements of fq star, such that gamma to the power of r plus 1 is equal to 1. So in other words, q is the set of elements whose norm over fr is equal to 1. There are exactly r plus 1 such elements, so we have exactly r plus 1 coefficients and cosets in the definition of S, so xq is the Peisert type graph of type r plus 1q. So it has the same parameters as yq2, and we show that the graphs yq2 of fr and xq are isomorphic. And a small sketch of the proof, if we consider the stabilizer of the 0 point in the affine plane in the underlying affine plane, then if the multiplication by an invertible matrix sends one generating set to the other, then two Peisert type graphs are isomorphic. And we use this fact, and the generating set S of FR of the graph YQ2 of FR can be obtained from S by multiplication from the left by any non-degenerate matrix sigma conjugate 1 1, where sigma is not equal to sigma R, sigma conjugate. It is not difficult to show that we have such an isomorphism, and the graph XQ, or equivalently YQ2, has some interesting properties, and we devote the rest of the talk to this graph. First, let us construct a non-canonical clique in XQ. So XQ is an extremal Peisert type graph because we have shown that YQ2 is extremal and YQ2 is isomorphic to XQ, and this but the special way to define XQ allows to define a non-canonical clique explicitly. Let's epsilon be a primitive element of FQ. Consider a two-dimensional F square root of Q subspace in FQ squared. So in our definitions for XQ and YQ2, R is always square root of Q. So R and square root of Q are interchangeable in these slides, in further slides. So we will see and we will meet different ways to write this. So consider the following two-dimensional F square root of Q or FR subspace in FQ squared. So the two vectors that generate this subspace are 1 plus beta and epsilon to square root of epsilon conjugate plus epsilon beta. Then if we write this as set, then write it as, we can write it as A plus beta epsilon conjugate plus A plus B epsilon beta, where A and B run over FQ F square root of Q. And in other words, it can be written like this: A plus B epsilon conjugate plus A plus B epsilon beta. And if A and B run over F square root of Q, then A plus B epsilon run over FQ. So we can use this definition. CQ consists of elements gamma conjugate plus gamma beta, where gamma runs over FQ. And it's easy to see that 0 belongs to this set. So it's given by the case when gamma is equal to 0. And if we factor out gamma, then we get gamma to the power of square root of Q minus 1 plus beta, where gamma runs over FQ. And So let me recall what was the definition of S. So delta ran over Q, where Q is the set of elements such that of all elements gamma such that gamma to the power of r plus 1 is equal to 1, but the element gamma to square root of q minus 1, where square root of q is just r, this element is equal to, if we consider its r plus 1 power, it's equal to 1. So the expression in braces belongs to S, and as well as multiplied by gamma. So CQ, this two-dimensional subspace CQ is included in S union 0. And the following facts about CQ hold. Proposition 2. The subspace CQ induces a non-canonical clique in XQ. Moreover, the intersection of any canonical clique in XQ containing 0 and CQ has exactly square root of Q minus 1 non-zero elements. These elements are given by the elements gamma lying in the same coset of F square root of Q star in FQ star. And as a corollary, we can have non-canonical cliques related to CQ. For any I from the set 0, 1, so on, square root of Q, the set epsilon I CQ, where epsilon is the primitive element of FQ, such a set epsilon to the power of I times CQ induces a non-canonical clique in XQ, and for any I and J such that I is not equal to J, we have that the intersection of these cliques corresponding to I and J is just the zero, contains just 0 element. And we classify non-canonical cliques in, so let us go back to the conjecture that the graph YQN has exactly r to the power of n minus 1 over r minus 1 non-canonical cliques containing 0. So we prove this conjecture in the case when n is equal to 2, and we show that this the square root of q plus 1 non-canonical cliques CQ epsilon squared CQ, so on epsilon to the power of square root of Q CQ are the only non-canonical cliques in XQ containing 0. And let us discuss a connection with affine polar graphs. Let V be a 2e-dimensional vector space over a finite field FQ, where E is greater or equal to 2 and Q is a prime power, provided that the hyperbolic provided with the hyperbolic quadratic form HQ of X is equal to x1 x2 plus x3 x4 so on x2e minus 1 x2e. The set HQ plus of zeros of HQ is called the hyperbolic quadric, where E is the maximal dimension of a subspace in HQ plus. This typo should be HQ plus. Denote by VO plus to EQ the graph on V with two vertices with two vectors x and y being adjacent if and only if HQ of their difference x minus y is equal to 0. The graph VO plus 2EQ is known as an affine polar graph or hyperbolic affine polar graph. And this, as Rees mentioned, this graph is strongly regular and the parameters are given on the slide. Let V of NR be an n-dimensional vector space over defined field Fr, where n is greater or equal to 2 and R is a prime power. And let F of x1, x2, so on, xn be a quadratic form over V of NR. Define a graph GF on the set of vectors of V of NR as follows. For any UV from V of NR, U is adjacent to V if and only if the value F of U minus V is equal to 0. And two quadratic forms, F1 and F2, with variables x1, so on, xn, and y1, so on, yn, are said to be equivalent if there exists an invertible matrix B from GL of NR such that F1 of Bx is equal to F2 of Y. And let F1 and F2 be two equivalent quadratic forms, so over the same defined on the same vector space, then the graphs GF1 and GF2 are isomorphic. And as a corollary, we establish one more isomorphism. The graphs XQ and VO plus 4 square root of Q are isomorphic. So the first isomorphism is the isomorphism of Y2, YQ2 and XQ. And the second isomorphism is the isomorphism of XQ and VO plus of 4 square root of Q. So from now, we have three equivalent definitions of VO plus of the affine polar graph VO plus 4 square root of Q. And let us discuss the tightness of the wave distribution bound for XQ in which is isomorphic to VO plus of 4 square root of Q. The tightness of the wave distribution bound for the negative non-principal eigenvalue. So this isomorphism establishes a connection with the talk of Rhys-Evans on extremal eigenfunctions of polar and affine polar graphs. So the connection is exactly in the case of affine polar in the case of hyperbolic affine polar graphs, and not all of them, but just VO plus 4 square root of Q. Let T0 be equal to Q and T1 be equal to Q beta. So Q is the set of all elements from FQ such that of all elements gamma from FQ, non-zero elements, such that gamma to the power of square root of Q plus 1 is equal to 1. And we know that T0 and T1 are subsets of the lines with slopes 1 and beta. So they are subsets of the cosets given by the coefficients C1 and beta. And these two lines do not, these two cosets do not belong to the set of cosets of the generating set of XQ. So these lines in terms of the affine plane, these lines do not intersect with S, and thus they are Coclicks in XQ. This means that T0 and T1 are Coclicks. Let gamma 1 be an element from T0 and gamma 2 beta be an element from T1. So these two elements are given from T0 and T1 belong to T0 and T1 respectively, consider the difference and take into account that Q is a subgroup of order square root of Q plus 1 in FQ star, and the fact that minus Q is equal to Q. It is not difficult to see that the difference belongs to S for any elements gamma 1 from T0 and gamma 2 beta from T1. This means that T0 union T1 induces a complete bipartite subgraph in XQ with parts T0 and T1 of size square. The parts have the size square root of Q plus 1. And we define a function. Rees calls such, as I remember, difference indicator functions. F of gamma is equal to 1 if gamma belongs to T0, f of gamma is equal to minus 1 if gamma belongs to T1, and 0 otherwise. And the function f, we show that the function f is minus square root of q minus 1 eigenfunction of xq, whose cardinality of support is 2 times square root of q plus 1. And corollary, the weight distribution bound is tight for the negative non-principal eigenvalue minus square root of q minus 1 of xq, which is isomorphic to the affine polar graph VO plus for square root of q. And the third open problem, which I would like to pose in this talk, is characterized minus square root of q minus 1 eigenfunctions of xq whose cardinality of support meets the weight distribution bound. I think this is a good open problem. And the last part of my talk is related to the connection of Peisert type graphs with affine polar graphs. Peisert type graphs with with orthogonal arrays. An orthogonal array OA of Mn is an m times n squared array with entries from an n element set W with the property that the columns of any 2 times n squared subarray consist of all n squared possible pairs. Sorry, just a moment. The block graph of an orthogonal array OAMN denoted by D of OAMN is defined to be the graph whose vertices are columns of the orthogonal array where 2 columns are adjacent if there exists a row in which they have the same entry. Let SRI be the set of columns of OAMN that have the entry I in row R. These sets are cliques, and since each element of the n element set W occurs exactly n times in each row, the size of SRI is n for all I and R. These cliques are called the canonical cliques in the block graph D of orthogonal array OAMN. A simple combinatorial argument shows that the block graph of an orthogonal array is strongly regular. Recently, we showed that each Peisert type graph of type MQ can be realized as the block graph of an orthogonal array OAMQ. Moreover, there is a one-to-one correspondence between canonical cliques in the block graph and canonical cliques in a given Peisert type graph. note that the size of the canonical cliques in the block graphs of orthogonal arrays meets the Divisors-Hofmann bound. Let OA of Mn, if OA of Mn is an orthogonal array with n greater than m-1 squared, then the only cliques of size n in the block graph are canonical cliques. This bound is given by the book by Gorges and Marr. Let m-1 be a prime power, then there exists an OA, an orthogonal array OAM m-1, and using McNeish construction, see page 98 of this book, it is possible to construct an orthogonal array with parameters m and m-1 squared from this array. This larger orthogonal array has OAM of OA of m-1 as a subarray, and thus the graph D of DOAM m-1 squared has the graph DOAM m-1 as an induced subgraph. Since this subgraph is isomorphic to the complete graph of size m-1 squared, it is this subgraph is a clique of size m-1 squared in the larger block graph, and this clique is not canonical. And this is the last slide of my talk. Problem 4 was posed by Gorges and Marr. Assume that OA of m-1 squared is an orthogonal array, and its orthogonal array graph, and so block graph. Sorry, okay. Its block graph has non-canonical cliques of size m-1 squared. The problem is, do these non-canonical cliques form sub-arrays that are isomorphic to orthogonal arrays with entries from 1 to 1m-1? So in our case, we have block graphs xq or equivalently yq2 or equivalently affine polar graphs VO plus 4 square root of q are block graphs of orthogonal arrays with non-canonical cliques, and they just correspond to the case described in problem 4. And it would be interesting if our extremal graphs would answer this problem in negative, but we have shown that the non-canonical cliques in XQ form sub-arrays that are isomorphic to orthogonal arrays with entries 1 square root of q. So we have not solved problem 4 from the book. So we have just found one more example of block graphs of orthogonal arrays such that their non-canonical cliques correspond to orthogonal sub-arrays. Thank you very much for your attention.
Thank you very much for your talk, Sergey. Are there questions to the speaker? Well, but as for the last problem, do you have any feeling about the answer? I mean, problem number 4. Do this non-canonical, cliques form? Yes. So, what is? Yeah.
It's a very interesting problem. Actually, we deal with when we consider Peisert type graphs and work with them. Actually, we work with underlying orthogonal arrays, and this class of orthogonal arrays comes from affine planes And this is an important class of orthogonal arrays. So because they have algebraic structure, but in general, orthogonal arrays may not have combinatorial structure, and so somehow our result can be explained shortly as follows: if we have nice algebraic family of orthogonal arrays, then the answer for problem 4 is positive. So it's very interesting to consider some other orthogonal arrays. Say we can try different affine planes that are not isomorphic to HG to Q. Probably this would be the next step in investigation towards this problem. Yeah, thank you very much for your question.
Thank you very much for your answers. There is one more question, which is coming from Akihira.
Hello, Sergey.
Hello.
Yeah, so I have several questions. First of all, what you call a Peisert type graph. If I understand correctly, this is a fusing of a amorphic association scheme, and it is already proved by Andrei Ivanov and also Igor Faradyev and Misha Kulin, that any fusing of amorphic association scheme gives a strongly regular graph. So this Peisert type graph, just fusing of amorphic association scheme defined by affine plane or Latin square or orthogonal array. Those are all the same thing. Yeah. And another question is about the non-canonical cliques of XQ you classified.
Yes.
And then after that, you show the isomorphism of XQ with the affine polar graph VO plus 4Q.
Yes.
Now, my question is that, well, in terms of the description of XQ, which is in terms of KV graph of a finite field, you can distinguish canonical and non-canonical cliques.
Yes.
But
for the
affine polar graph, can you distinguish canonical cliques and non-canonical cliques?
Yes, this is a very good question. The definition of canonical cliques is motivated by the Erdős-Karada theorem. And for example, if we consider a block graph, if we consider an orthogonal array, then we consider some row and we fix some entry. And we consider all the columns of the array that have fixed entry in the fixed row. So somehow this is a canonical family of intersecting columns. And in this sense, this definition is natural.
Yeah, but it depends on the description of the graph. If you have a different description, so I wonder how you could describe canonical and non-canonical group in terms of geometry of the affine polar graph.
As I understand the situation, so this is work in progress, and we think about this question as well. My understanding is that there is a partition, there is a natural partition of the set of cliques of a affine polar graph into two parts. And So this isomorphism with affine polar graphs makes new questions. So canonical cliques. This means canonical cliques cannot be easily defined for all families of strong irregular graphs.
So let me put it in a different way. So if you map canonical if you have a non-canonical cliques in XQ, that means you have those cliques in the affine polar graph. Now, can you prove that the full automorphism does not map a canonical clique to a non-canonical group, non-canonical clique? They are not equivalent under the automorphism group of the affine polar.
As I know, they must be equivalent under the automorphism group.
Equivalent?
Equivalent, yeah.
Well,
as I know, all maximum cliques in affine polar graphs are equivalent.
Yeah. I see. That's so. Then for the graph XQ, well, you could define canonical and non-canonical, but they cannot be distinguishable in the geometrical language.
Yes, we together with my co-author Chiho Ip, we have discussed this this question, exactly the same question. So the definition of canonical cliques and this research direction was proposed by Gorges and Marr in the book I mentioned several times in my talk. Erdos-Corrado theorems, algebraic approaches, and they define canonical cliques for some families of strong irregular graphs, in particular for block graphs of orthogonal arrays and for polygraphs of square order, discussed today several times. And for us, it was also a surprise that we have such an isomorphism with another family where the notion of a canonical clique may make no sense.
Right. Yeah. So it's a little bit strange that it's not invariant under the automorphism.
Yeah. So
anyway.
I think that we will inform Gorges and Marr about this because somehow this is a general problem. So if I would define canonical cliques for affine polar graphs, I would say that the generators are just the canonical cliques containing zeros.
Yeah.
But it does not agree with the definition of canonical cliques in the case of orthogonal arrays.
Okay, thank you. Yeah, but so this is just for n equals 2.
Yes. At least for n equals 3, we have a family of graphs. Computations show that this is not, it has parameters of a affine polar graph, but it is not isomorphic to a affine polar graph.
I see.
And we know that affine polar graphs are rank 3 graphs, but our graphs Y, U, N, also according to computations, I think we can show this, that they are co-H transitive, and computations show that they are not H transitive, so they are not rank 3. And if we can show this this property, this would distinguish these two families of graphs, affine polar graphs and YQN.
Yeah, not isomorphic. Okay, yeah. Yeah. So for larger n, you have a conjecture on the number of non-canonical cliques.
At least 2.
Yeah. This conjecture 1.
Conjecture 2.
No.
Number of non-canonical.
Yeah, the number of non-canonical.
Yeah.
Conjecture 1.
Right. Yeah.
Yeah. And you prove this conjecture for n equal 2.
Yes.
Right.
But this can be probably derived from the properties of polar spaces as well.
Mm-hmm. Yeah, but for larger n, do you have this many non-canonical cliques? Do you know there are at least this many non-canonical cliques?
We have not obtained any result, any theoretical results on this direction. Only computations.
I see. Okay, thank you. Final question. Can you show me once again the definition of an extremal graph?
Extremal Peisert type graph without strict EKR property.
Oh, yeah. So you say X is extremal if all Peisert type graph of type m-1. So X has type MQ.
Yes.
So extremal means all Peisert type graph of type m-1Q, but if you have a X which is type MQ, then you may delete one coset to get a subgraph.
Yeah, we assume that X does not have a strict EKR property. So X itself does not have strict EKR property. And if all graphs of Peisert type graphs whose number of cosets is 1 less, if all of them do have strict EKR property, then we say that X is extremal.
Yeah, so this is the property of the integer m, not really about X, right? So you're talking about the smallest positive integer m such that all Peisert type graph of type m-1Q have the strict EKR property. Is that right?
Yeah. But
so
I think
when
this can be regarded as a property of M and as well as a property of a graph, because there are Peisert type graphs with the same parameters that do have strict EKR property. So not all.
Okay, that I understand. But my question is, when you talk about the Peisert type graph of type m-1Q, you not only consider subgraph of X, but all possible Peisert type
all
graph.
Possible, not only subgraph.
That was
in the
question.
Case of subgraphs, we could say we could speak about minimality of Peisert type graph. And this is also one of the problems.
Okay, thank you very much.
Thank you very much for your questions and comments.
Okay, any other questions? Well, if not, then let us again thank Sergey for this very interesting talk, and Akihiro for discussion about some definitions and problems and results around of extremal Peisert type graphs and so on. So let me also thank all